Getting ready for the International Olympiad of Artificial Intelligence? Well, you're in the right place. Let's dive straight into a genuinely crucial concept for your exam prep and unpack the math behind mutual information. Figuring out exactly how different variables interact is an essential challenge in data science, so let's break the whole thing down together. Here's a quick look at our agenda for this explainer. We'll be covering 1. The core problem, 2. Defining mutual information, 3. Step-by-step probability tables, 4. The zero-change scenario, 5. Handling continuous variables, and 6. The connection to entropy. Section 1. The core problem. Okay, to start, we really have to understand why we even need this metric in the first place. Imagine we want to predict if someone absolutely loves the cult classic movie Troll 2. Now, we have a continuous variable like their height, right? But we also have discrete categorical variables like a simple yes or no answer to whether they like popcorn. If we try to use a standard metric like r² to figure out how these variables relate to loving Troll 2, we literally hit a brick wall. Why? Because r² only works with continuous data, and our popcorn data consists of discrete yes or no answers. So how in the world do we actually quantify this relationship?
Section 2. Defining mutual information.
This is exactly where our hero metric steps in. Mutual information is so fascinating because it gives us a hard numeric value that shows how closely related two variables are. It handles mixed variables beautifully by quantifying exactly how much one variable can tell us about the thing we're trying to predict. But to actually calculate it, we've got to understand the specific probabilities that make up its equation. First up, we need to look at joint probabilities. This is, exactly what it sounds like. The probability of two things occurring at the exact same time. For instance, if we look at our data set and see that 3 out of 5 people both like popcorn and love Troll 2, our joint probability for that specific combination is just 3 divided by 5. In contrast to that, marginal probabilities only look at one single variable entirely in isolation. So if we just want to know the probability of someone not liking popcorn, we simply count them up. If 2 out of 5 people in our dataset don't like popcorn, our marginal probability is 2 divided by 5. Or if 1 out of 5 people simply doesn't love Troll 2, well, that marginal probability is 1 divided by 5. Make sense?
Section 3. Step-by-step probability tables.
Now, let's look at how this builds into the essential probability tables you absolutely need to master for your exam. Keeping your data perfectly organized is the secret here. Step 1, calculate joint probabilities for all those combinations. Step 2, place those joint probabilities right in the center grid of your table. Step 3, just add those joint probabilities across the rows and columns. And Step 4, place the resulting marginal probabilities in the margins. Let's actually look at this in practice. When you look at this layout, you'll see it perfectly matches the mathematical terminology we just talked about. By filling out the columns for likes popcorn and the rows for loves Troll 2, you can instantly see why marginal probabilities are called marginal. They literally sit right there in the margins of our joint probability data. And here's a great check for yourself. You can calculate a marginal probability directly from the raw data, or, as we see right here, you can simply add up the joint probabilities in a specific row or column. They will both give you the exact same fraction. Once that table is completely filled out, we take those probabilities and plug them straight into the mutual information equation. It uses two summations, which basically means we create a calculation term for all possible combinations of our variables. Yes, 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 no, no, yes, and no, no. For every single term, we take the joint probability and we multiply it by the natural log of the joint probability divided by the marginal probabilities. But hey, listen up, because here is a brilliant technical trick to keep in your back pocket for the IOAI exam. If you have a 0 in your table, you might end up trying to calculate the log of 0, right? Which is mathematically undefined. However, as x gets close to 0, x times the log of x approaches 0. So if your numerator creates a 0 in that fraction, the entire term just cleanly evaluates to 0. It's a tiny edge case, but it is vastly important for getting accurate calculations. So after expanding the summation and crunching the numbers for all 4 combinations of our popcorn and Troll 2 data, our total mutual information comes out 2.22. Now this is a baseline numeric value. By itself, yeah, it's just a number. But we can now calculate the mutual information for other variables in our data set and compare them to this 0.22 to see which variables are actually the most useful for our predictive models. Section 4, the zero change scenario. What's really interesting is how we can stress test this equation by manipulating the raw data. What if the likes popcorn variable literally never changes? Let's say every single person in our dataset likes popcorn. So likes popcorn is exclusively yes. Well, that means the entire no column in our probability table just becomes completely filled with zeros. And if we take that modified table, expand the summation for all combinations, and run it through our natural log equation, the resulting mutual information drops exactly to 0. Why? Mathematically, this happens because the joint probability now exactly equals the marginal probability, so dividing them just gives us 1. And since the natural log of 1 is 0, the whole result just zeroes out. Which brings us to a beautiful conceptual rule. If one variable never changes, like if everyone always likes popcorn, it can't possibly tell us anything about why someone's opinion on a movie is changing. 0 new variation means 0 mutual information. Keep this conceptual rule top of mind as you're doing your practice problems. Conversely, let's play with the data so both variables change perfectly together. If likes popcorn is yes exactly when loves Troll 2 is yes, the mutual information jumps up to roughly 0.5. That's a lot higher than our original 0.22. But here's the kicker. If we flip it so that likes popcorn is yes exactly when loves Troll 2 is no, meaning they are changing in the exact opposite ways, the mutual information is still roughly 0.5. It actually doesn't matter if the changes are exactly the same or exactly opposite. Because the changes in one column perfectly predict the changes in the other, both scenarios give us a really high mutual information score. Section 5. Handling continuous variables. But wait. Earlier we noted that mutual information is fantastic for mixed data. So how exactly do we apply this discrete grid-like table method to a continuous variable, like human height? The solution is incredibly elegant. We simply create a histogram of the continuous values. By splitting that continuous data up into distinct bins, we can basically treat each bin as its own discrete category. So if we divide height into 3 bins, we suddenly have 3 columns of joint probabilities that we can plug right back into our table. Since we have 3 columns and 2 rows, meaning Troll 2 is yes or no, when we expand our equation, we'll just have 6 terms to add together instead of 4. It's the exact same math, just adapted visually. Section 6. The connection to entropy. Let's move to our final conceptual pillar, which is vital for Olympiad-level understanding. If you look closely, that slightly nasty-looking double summation equation for mutual information is actually derived directly from the equation for entropy. Structurally, they are both built heavily on sums of probabilities multiplied by logs. And this mathematical similarity isn't just an accident, it points to a much deeper shared concept. To summarize it conceptually, both of these metrics essentially measure surprise. Entropy measures the total surprise in a single variable. Mutual information captures exactly how much the surprises in 2 different variables overlap. Think back to our zero change scenario. If there is no surprise, no change at all, there is 0 mutual information. But when the surprise is greater than 0 for both variables, and those changes are related, mutual information captures exactly how much those surprises are linked. So, as you continue your exam prep and tackle your next dataset, ask yourself, what hidden variables share overlapping surprises, just waiting to be discovered? Keep looking for those shared surprises, and you're going to master these probabilities in no time.